Welcome to my presentation on the atmospheric river event, WSP's emergency response to the washout at Falls Creek, Highway 1, BC, Canada. Just a couple of housekeeping items. This presentation is available for download in your handout section and on the webinar tool. And there will be time for questions at the end. So please enter your questions into the comment box or question box. Okay, so we'll get going here. So my name's Glenn Rutherford. I am the Director for Ground Engineering for Vancouver Island, the BC Interior and Yukon with WSP. I'm a geotechnical engineer by trade. My key areas of expertise are around kind of risk change and project management. I do a lot of kind of conventional geotechnical engineering, rock mechanics, soil mechanics for linear infrastructure. I have about 30 years experience in the industry. And I reside in Kelowna, BC. Here's a nice little photo of Kelowna for those interested in the interior of BC. So we're going to be going over our key highlights, a little bit about the event, some key challenges, talking about the abutments and channel reconstruction. We're going to talk about some innovations, some key takeaways, and then we're going to have some time for question and answers. Okay, so the Falls Creek washout, my client was the BC Ministry of Transportation and Infrastructure. This site is located just south of the town of Lytton on Highway 1. This is a steep, narrow gorge type valley with kind of the highway perched up on the side of a hill up and adjacent to the rock face. The afternoon of November 15th, 2021, we had what we call an atmospheric river pass through BC. This event caused flooding, washout, and damaged 18 sites along the Highway 1 corridor, along with kind of many other sites on kind of several other routes. This talk is specifically about one of those major culvert washouts. WSP had worked on multiple other sites for MOTI, mostly closer to Hope and Vancouver. So what is an atmospheric river? So I got this nice little graphic from the kind of one of the local news services here. But it's basically a large stream of water vapor that is excessive in size. It pumped a significant amount of rain, and if you look at that, it actually shows it's like twice the volume of the kind of Amazon River. So what did it do? So this, when it crossed across the kind of BC area, so this is Vancouver Island, this is Vancouver right here. So across Vancouver Island did some damage to Highway 1 and Highway 19. Went through the lower mainland, started pushing up against the mountain ranges and really started dumping water at that point in time. It impacted kind of Highway 7 and Highway 1 in around Hope. Our site is right up here by Lytton, and it impacted Highway 5, Highway 3, and Highway 99. If you notice, it basically cut off all the highways and accesses to the interior, to the rest of Canada. So my first impressions of the site is this wonderful photo. You can see that there's a significant kind of removal of material for the highway. Someone was nice enough to park a nice little scale vehicle right on the edge of the the kind of washout. This is 20 meters deep and 80 meters wide, and it's thought to be caused by plugging of the culvert and caused overtopping and downcutting of the highway embankment fills. So this site is quite steep, and this is a drone photo here of the Falls Creek area. If you notice along the side, this was impacted by a fire in 2020, and that turns the soils hydrophobic, which creates more runoff than normal. It also increases the amount of debris that impacts or can get washed down. So it's likely that the culvert was appropriately sized kind of for a climate change design state. However, with kind of our changing climate normals, we end up with higher intensity events. So here's a photo of kind of looking up from the bottom of the embankment. You can see that there was a culvert in the bottom, but you know, basically the down cutting has kind of exposed that culvert. So what our primary challenge was restoring access, but in a way will be conducive to the rebuild. A lot of problems with timing. There's ongoing repairs to rail line at the bottom of the kind of the embankment, which you don't want to have construction on the kind of this upper steep slope if we have people working around the bottom. So there had to be coordination there. We had some near vertical scarps on either side. We had to retrain this creek to go back into the culvert on a temporary basis so we could recreate the slopes and abutments. The team quickly identified that an acro bridge could be used for temporary access, but from a geotechnical perspective, how to deal with the differing foundation conditions. We had fill on the north side, which is on the left of your screen or the photo, and then bedrock and fill on the right side of your screen. And then there's weather. This event occurred in November, which is kind of winter in Canada. So this posed problems for construction because of various different weather events. So we went from kind of beautiful blue skies to kind of feet and feet of snow, and it changed on a daily or weekly basis, which had made it quite difficult for the construction crews. So on the south abutment, we had this weak rock. It was heavily weathered. In order to hold it together, we identified that we needed to bolt it together on the side. We also needed to build up the outside edge of the foundation area. So there's bolts in here as well. And this shotcrete was able to, we ended up using some baskets as well, was able to build up the foundation for the acro bridge, which ended up being basically just lock blocks on top of our kind of foundation fills. And then that translated over onto the kind of the north side, which we ended up having to regrade this entire slope. This slope if you recall from the earlier pictures, was near vertical up at the top here, and there had a creek down the bottom, and so we had problems with kind of having enough space to get a safe slope in here, and just safety issues cutting down the vertical top bits. So the geometry here was critical because we only had the maximum span of the Acro Bridge was 80 meters, and that's pretty much all we had. So we had to kind of make sure that we were kind of fighting for kind of every kind of every meter that we could get here. So we had very tight control of the geometry, and that goes into this channel reconstruction. So in order to kind of get that fill slope in, we needed to retrain the channel and temporarily divert it back into that culvert that was damaged at the bottom of the slope. And it shows kind of, it was difficult for us to get enough space to get the appropriate kind of channel width or new channel width for the permanent condition into the bottom here and get our appropriate slopes. So the hydrologists here had utilized kind of the increased factors for kind of our peak flows in order to design this culvert or this channel at the bottom, and the riprap on that kind of defined our kind of slope geometry. So we had to pick how high that channel had to be in order for us to actually achieve the appropriate angles on the slopes. And I think that this really could have gone better, but this is a very personal opinion. If WSP was both a geotechnical engineer and a hydrotechnical engineer, because we could have had better communication between the two disciplines and really worked together to try and get this iterative process going as fast as possible, because time is of the essence in these emergency responses. Okay. So our key innovations here. WSP had a very rapid response to this. We had kind of early selection of the Acro Bridge. The concept was key to meeting this delivery schedule. There were several different iterations of kind of solutions, and from a geotechnical perspective, I would have actually liked to kind of swung down kind of the side of the bank and kind of cut up, but there were some problems with that from other disciplines. Yeah, we had great team communication to realize and accept project risks. As you could imagine, there's a number of kind of risks associated with kind of just trying to fix this. We had kind of steep slopes on either side, or steep rock slopes on either side with rockfall risks. We had reduced factors of safety for temporary slopes. These are generally covered within the kind of our bridge code, but it was trying to get everything to work within that. We had this interactive design with the bridge contractor on the foundation design for the temporary structure, and that's like I was talking about with especially with the kind of the south foundation, where we ended up having to try and build up the one side of the kind of foundation area in order to get enough bearing area for the high load bridge structure. And then a lot of interdisciplinary coordination was required to identify various rapid solutions. And like I said before, the interactive slope and channel design to fit everything within the available geometry was probably my biggest challenge in this one. Once we kind of get that geometry pinned down, and you got to remember that typically we're doing this without the benefit of a lot of intrusive investigation as an emergency response. So we had to do a lot of estimating in terms of material properties, et cetera, to make sure that we kind of really knew what was kind of how it would perform. And then, once we got the kind of the bridge in and open, WSP carried out a follow-up investigation for basically a factual investigation that with intrusive boreholes to try and identify the soil parameters and also the kind of the bedrock structure. And interestingly enough, we found that this highly variable bedrock conditions. The quality of the bedrock varied significantly, and the geometry of the bedrocks varied significantly. For example, on the where we see on the north side with the drill right in the foreground there, the photo. We drilled one hole and hit rock. I think it was around 8 meters. We stepped off about 3, maybe 2 meters, kind of to the riverside, or basically to the west, and we found, because we had some problems in the one hole due to the rock quality, so we moved over, and lo and behold, we ended up not hitting rock until somewhere around 15 meters. So in that 2 meter span, we changed kind of rock elevations from 8 meters to 15 meters. And one of the kind of big things here is this follow-up investigation. So the BC Ministry of Highways had a number of these sites, and so they chose a delivery method, which is kind of the alliance model for delivering these projects. And this alliance model allows a lot of integration between the owner, the consultants, and the contractor to really get things moving as fast as possible. Okay, so my key takeaways. We really want to be super flexible in your design in these emergency responses. We've got to allow for other disciplines, limitations. Like I said, when we wanted to keep to have cut down the bank and then back up the other side, we shortly found out when talking to the kind of the highway designers that this would require significant grades that were incompatible with the kind of the winter truck traffic that's expected on this hill. So it's basically an excessive of 8%, which is not conducive to the environment in that area. And then, like anything, it always takes longer than you think. The original schedule was to have us finishing the temporary access in early January. You've got to remember that the event happened in November, and it took a few days for even the the emergency responders to be able to get to this site because there were so many breaks in the highway before this. And so, yeah, you know, we had this kind of wonderful schedule to push on and get everything done in early January, but like I implied before in the presentation, the weather just didn't get the memo. We had a number of kind of heavy winter storms roll through that significantly reduced the kind of the speed of assembling that acro bridge. I remember coming on site and looking at it and seeing, hey, the you know, like the workers are having to use torches to thaw out the bolt holes on the acro bridge so that they could even start assembling it. And then, you know, like, don't rush or skimp on your planning and safety in these kind of emergency situations. A nearby site, not the highways, had several injuries and delays due to inadequate planning. Too many people taking too much risk. It's just not worth it. The BC MOTI was working diligently on this recovery, on the recovery work and identifying new hazards and inventorying their linear system. I wanted to talk about SRIVA, which is WSP's Climate Risk and Vulnerability Assessment Solution. This tool is a kind of a GIS-based climate predictor that shows or identifies risk levels for various structures or linear assets. And if you want more information on that, please contact Chris Lander. He's a senior meteorologist with WSP, and I put his email address in here, or you can contact me. So, okay, so that's the kind of end of my presentation, and we're ready for some questions.
Thank you, Glenn, for this presentation. Just mentioning quickly the housekeeping items. The presentation slides are available to download in the handout box as a PDF, and also please continue to log your questions in the question box on the GoToWebinar control panel. I will start with the first question. What was the final solution? Was it a bridge structure or a larger culvert that could pass flow and debris?
Yes, and so eventually, well, not eventually, I think that we came to a realization that in these very large fills, like there was 20 to 40 meters of fill on top of this culvert, that structure is very, very vulnerable to this climatic change scenario. So the final solution is a bridge structure. And it is so that channel that was constructed and will end up being at least part of the final solution.
Thank you. What were the environmental protection consideration during the work?
So there was a environmental consultant on site at all times during the construction work, and there was some attempts to maintain kind of or minimize the amount of sediment getting into the river. There was identification of kind of you know, like there wasn't any bird nesting at that point in time, so there were because of you know, November in BC. But there was, but that was kind of thought about and assessed. You know, the difficulty with the environmental considerations, and it's kind of frustrating in these situations, is that no matter what, a significant amount of sediment is going to get into the river because of the event. But steps were taken to minimize that.
Thank you. Are the permanent abutment and sidewalls carried out?
Well, that's actually a really good question. So the right now, the permanent situation is still in design. I believe the kind of the alliance solution. So I was part of the kind of emergency response end of it. And then there's within the BC system, there's a recovery phase following the response phase. And so we put in the temporary structure, and since we got that in, they have been working diligently on creating a final design and putting in kind of foundations for the final solution. So the last I heard, which is just last week, they had started piling on kind of the abutments for this structure.
Thank you. What is the link between forest fire activity, climate change, and events like this?
Yeah, and so it's really interesting because you would originally think that kind of what does a fire have to do with this, but as I mentioned to you earlier on, that the once you change or you burn the area hot enough, it turns the soils in the area hydrophobic, so basically more runoff happens. And that lasts for kind of years and years following a fire until it kind of breaks down that hydrophobic structure. So that increases runoff. So with climate change, we have increased the increased volume events. We have shorter duration but higher volume events, and we have this higher potential for forest fires because we end up with extremes both in kind of the wet events, but we also have extremes in the dry events as well. And so especially in the kind of the BC interior, you end up with these kind of high fire risk areas. And Lytton has been hit so hard. It's terrible to because they were hit by a fire which actually burned half the town in 2020, just before all of this happened in 2021. And it's quite devastating in terms of how that has further contributed to kind of other events in the area, where we end up with this increased runoff, higher duration flows, and more debris that ends up. And so you can see how culverts like this, even as large as they can potentially be, are highly at risk.
Thank you. I will take the last question. What would you have done differently, if you can share with us?
I think that in an ideal world, I would have had kind of more staff, and it's really difficult in this location to access. This is fairly remote location, especially since, like I said, Lytton had burned. So having more staff stationed closer to the site, I probably would have looked at the overall risk of rockfall and kind of further debris flows in the area. We did look at it, but I think that we should have probably done a little bit more on that as we move forward, because that changes over time and with weather patterns. So in hindsight, we probably should have done the kind of risk assessments again. And like from that was probably from my perspective, um, uh, but I think from the ministry's perspective, and they would have liked to give this solution sooner. And so I think that they, you know, like if they do their deep dive on it, that they would look at ways to kind of function in extreme weather events that we end up having following this event.
Thank you. Thank you, Glenn,
Okay.
for a great presentation. Thank you, everyone, for joining us today. Please feel free to follow up directly with Glenn via the contact details shown on the screen. So have a nice day, everyone. We will wrap up the session now. Thank you.